Hi, I'm Chris Feda. This is my project on the wall follower simulation using Weebot simulations. So the goal of this simulation is to have this bot drive along this jagged wall for 1 minute while maintaining the requirement of 50 centimeters away from the wall as long as possible. If we look at the bot, we can see that there's a layer of sensors on top of two motorized wheels and a support wheel. Here we have a diagram of the sensors. We have a front and rear section. Each sensor is labeled individually, so we can use that in our coding part of the simulation. Specifically, we use the SO3 as the front sensor and the SO0 as the side sensor. Since the bot has sensors, you can assume it's going to be a closed loop system, which is actually a good thing. The closed loop system can correct itself because it's relaying information back into itself using those sensors. This means it can eliminate any noise and error. Since the system is closed loop, it means the system is linear. With linear systems, we can use PID controllers more effectively to tune and optimize the system. Since a PID controller is applied to the system, we can assume that the model is going to be a simple feedback system. To create the model, we need to get the equations of motion of the cart, which will allow us to get the transfer functions. On top of that, we also need to get the KP, KI, and KD gains for the PID controller. When we have these values, we can attempt to tune the system, which will increase the performance of the bot, which, like I said earlier, performance of the bot is following the path of the wall while also maintaining the 50 centimeters away from the wall. So the feedback model can be tuned using the auto-tune method. The auto-tune method is personally my favorite because the computer will do all the work for you. Once you have the transfer function plugged into the system or the model, you can tune the PID block and it'll allow you to tune the system effectively without much labor. The following image here is a feedback system mock-up that I made. It's very simple. You have your input data, which is attached to the PID controller and your transfer function. But what you'll notice is actually the line that goes back into the system. This is the sensor portion of this model. It is relaying information back into it and subtracting the error so that way it can get more accurate results. So I use the auto-tune function Simulink to tune the PID controller of the mockup system I made here. You'll notice from the output, we have a nice smooth curve after doing the auto-tune. The curve does not go over the horizontal line, or else that would mean the system's unstable and the car is overshooting its goal, which that's not good because it's not meeting the requirements. So the biggest concern that I have for the system after examining it for a while is actually the speed of the bot. Starting out, the bot will drive up to the wall and turn and follow the smooth walls pretty effectively. But once it reaches this area with the jagged corners, the bot will sometimes go a little too fast and not be able to slow down in time to be able to turn. So when troubleshooting, I would definitely adjust the velocities and play with it a little bit to sort of make it so it can slow down enough just so it can turn before advancing again. Because you want to always maintain that 50 centimeters away from the wall at all time, because that's the goal of the simulation. You can't go from this corner and drive straight across. That would have ruined the performance. It would not be following the goal. The problem with the system, so the system in a realistic, not simulation setting, you're not accounting for any disturbances. So if there was like bumps or like wind, any other elements that could come into play that would affect the positioning of the spot, this system does not account for those disturbances. So even though all this information is kind of oriented towards this specific simulation, there are a lot of real life applications, such as little vacuums that can go along the floor on their own. Those will use a system similar to this, because there'll be a lot of obstacles on the floor they got to get through, or if they're going to get close to a wall, it has to slow down before it ends up injuring itself. Also, self-driving cars are becoming a thing. While those systems may be a little bit more complex, it's along the same lines as this, where it's a closed loop system. It'll relay information through itself to correct itself. I'd say the biggest difference with those would be that they account for disturbances, which is extremely important for something like a car or a vacuum. So that way, for like specifically with the car, it doesn't injure the passengers that are inside it, as well as not damaging anything out in the environment.